Hello friends, Namaste and Jai Hind. Welcome to my show Technology and Engineering Made Simple. In the last lecture, we saw impulse function. There is one important property of impulse function is it has a discontinuity. As it is mentioned in its definition, its width is 0 and amplitude is infinite. Therefore, the derivative of impulse function doesn't exist. Now, derivative is nothing but variation of function with respect to variable. Since impulse function changes to infinity in 0 time, its derivative becomes infinite. It means derivative doesn't exist. So this is called discontinuity of impulse function, or it also represents discontinuity in other functions as well, which we will see in subsequent lecture. Now this statement can be seen in other way around as well. Whenever derivative doesn't exist, a function has a discontinuity, and this is a basis for today's discussion. In today's lecture, we are going to focus on exponential function, which has exactly opposite property of impulse function, which is called smoothness. The reason being, the infinite order derivative of exponential function exists, which means there is no discontinuity in exponential function, and hence it forms a very important modeling function in electrical engineering and various subjects associated with the electrical engineering, like signals and systems, control systems, signal processing, and so on. Now let's define exponential function. It is defined as f of t is equal to e raised to t. If you plot this function, you'll see a rising function with respect to time with value 1 at f of 0 equal to 1. Similarly, there is an exponentially decreasing function which is defined as f of t is equal to e raised to minus t, and the graph will look something like this, where the value will start decreasing with respect to time, and at f of 0 is equal to 1. Now what is peculiarity or important characteristics of exponential function? So if you take a derivative, it still remains e raised to t. In case of exponentially decreasing function, minus 1 will get multiplied, but the function still remains e raised to minus t. Only magnitude and phase will change. However, the shape of the signal remains same. And the shape of the signal in electrical engineering is nothing but the information in the signal. Other way around, in frequency domain, the frequency content remains same whenever the shape remains same. So here, if you see the higher order derivatives or nth order derivative of exponential function, it still remains same. Infinite order derivative exists and the function still remains same. So here we observe three important properties. Derivative exists, higher order derivative also exists, or one can say infinite order derivative exists. This is the second property. And the third property, even for first order as well as higher order derivative, the shape of the function remains same, which is a very important property. And such a function is called eigenfunction. There are some other functions which also exhibit such a property called sine and cosine functions, and they also form the eigenfunction. We saw the operator as a derivative and integration. These operators one can visualize as a system. So whenever you pass exponential function through a system, linear time invariant system, the output still remains same. So derivative and integration operator doesn't change the shape of the function, and hence they are called eigenfunction. Now if you see the integration, it still remains same, and similarly you can apply second order, third order, or higher order integration and it will still remain the same. And that is an important property of exponential function. Now we'll see another important model called power series, and then we'll connect with the exponential function. A power series is a polynomial of x with increasing power. So it is expressed as f of x equal to a naught plus a1x plus a2x square plus a3x cube and so on. So one can represent this in a compact form as well. There is another important model called Taylor expansion. Taylor expansion is nothing but a power series only, where the coefficients are given by derivative operator. So we'll see Taylor series in another lecture in detail. So right now, make an assumption you know the Taylor series, and the Taylor series for e raised to x is defined as 1 plus x upon 1 factorial plus x square upon 2 factorial plus so on. Now that can be represented in a compact form as n equal to 0 to infinity x's to n upon n factorial. Now, here if you apply the derivative operator, so derivative of e raised to x, then the first term will become 0. Second term, x upon 1 factorial will become 1. The third term, 2x upon 2 factorial, 2 will get cancelled and you'll get x. So if you take a derivative, you'll get a same series again. And therefore, the derivative of e raised to x remains e raised to x. So that is a proof for verifying when you operate on e raised to x using derivative, it remains same. Now we'll see another version of exponential function, which is slightly difficult to understand, which is called complex exponential function. F of t is equal to e raised to jt. Now, is it possible to draw the graph for e raised to jt? So here, we'll try to interpret e raised to jt in a different way, and then we'll apply physical interpretation to visualize this function. So first, try to understand what is a j. So j is a square root of -1. It is again an abstract model to represent complex numbers where square root of -1 cannot be defined. So it is considered as an imaginary number. Now your number system will have a real part and imaginary part. Now initially, though it sounds abstract, it has a physical interpretation as well, which we will see. How do you represent j? So j can be represented as j is equal to e raised to j pi by 2. According to Euler identity, it is written as cos of pi by 2 plus j sine of pi by 2. Now cos of pi by 2 is 0, sine of pi by 2 is 1, and therefore you get the original expression as a j. But what is a physical interpretation here? So j represents a phase of pi by 2. Now let's have another interpretation of j. So j square is equal to -1. So it represents phase of pi. Now we'll focus on physical interpretation of e raised to jx, and we'll try to plot e raised to jx. Now how do you imagine a plot of e raised to jx? So try to imagine another representation of e raised to jx as e raised to j theta. We can simplify it further as r into e raised to j theta, and this is a very popular representation of a circle in a polar form. So r into e raised to j theta. So if you know the equation of a circle, x square plus y square is equal to r square, and if you write it in a polar form, you'll get r into e raised to j theta. Now that can be compared with e raised to jx or e raised to jt. So here r is 1 while theta is your x. So theta is typically equal to omega t, where omega is a angular frequency which represents how many revolutions are completed in 1 second. Now we'll try to plot r into e raised to j theta, which is nothing but e raised to jt, where r is equal to 1. If you plot this with respect to r, so you can substitute the value of r is equal to 1. So you'll get e raised to j theta, and theta will act as a x. So it represents a circle. This is a, you can say, overall physical interpretation for e raised to jx. And now you can make it very generic by substituting any value for x. If you go in details of these functions in terms of theta, which is equal to omega t, and if you try to plot with respect to time instead of theta, because theta is repeating itself after 2 pi or 360 degree, but time is always increasing. So how that graph will look like if you plot a graph with respect to time instead of theta. So what we'll do, we'll take a different time instance on this circle represented by orange dots, and we'll project on magnitude time plane. So here, if you draw this and if you plot, you'll get a sine wave as a e raised to j theta. So here we are moving in anti-clockwise direction, and therefore we got a function e raised to j theta. If you draw e raised to minus j theta, so negative angle is represented by moving in a clockwise direction. So if you move in a clockwise direction, you'll get a second function e raised to minus j theta. Now if you multiply e raised to minus j theta with -1, these two sine waves will superimpose and their magnitude will become 2. So it will become 2 sine theta, and therefore you'll get a new equation. 2 sine theta is equal to a raised to j theta minus e raised to minus j theta. And therefore, you'll come across a popular identity called Euler identity or Euler identity, sine theta is equal to e raised to j theta minus e raised to minus j theta divided by 2. So here there is a small error. The j is missing, but it represents a phase. So why j is required in the denominator? You can take it as a homework problem. Now we'll see time domain versus frequency domain. Now here we draw a sine wave. So what is a time domain? Time domain is a plane where y-axis is a magnitude and the x-axis is a time, and we are looking at a graph perpendicular to this plane. So you are in time domain. Now similarly, you can define a frequency domain where y-axis is a magnitude and x-axis is a frequency. And then we are switching from time domain to frequency domain and frequency domain to time domain with the help of a mathematical tool called Fourier transform. But before we discuss Fourier transform, try to understand a physical interpretation for time domain and frequency domain. So in time domain, when you draw the sine wave, which we already saw in this, y-axis is your magnitude while x-axis is your time, and you're looking perpendicular to this plane that is called time domain plane. So you get a shape of the signal. Sine wave is also a function of frequency. So if you introduce third axis as a frequency axis, and then you draw this sine wave, assuming its frequency is 1 kilohertz, you'll get a small error if you draw at origin, because it will indicate frequency is 0. So the correct representation is you have to shift a sine wave at a frequency value of 1 kilohertz in this fashion. So now this is the correct representation of a sine wave after introducing frequency axis. We can see how to switch from time domain to frequency domain and vice versa. So in time domain, you are looking perpendicular to magnitude time plane. So in frequency domain, you will look perpendicular to magnitude frequency plane. So how do you do that? So you rotate frequency axis by 90 degree in anti-clockwise direction so that the time axis will go inside the board and it will look something like. Now in time domain, we remove or we don't draw frequency axis. Same concept one can apply in frequency domain, that is remove time axis. So you'll get a 2D plane instead of a 3D plane. So if you look into a 2D plane, then the sine wave will look like an impulse function. And here you can see this impulse function, which we already discussed in previous lecture, with magnitude or height equal to 1, which is the amplitude of the sine wave. We'll correlate this frequency domain representation with Euler identity. Now in Euler identity, you can see the sine wave has two sine components. One is e raised to j theta divided by 2, and second one is a minus of e raised to minus j theta divided by 2. So here we are having two sine waves in exponential domain, e raised to j theta with amplitude half. One can correlate with this trigonometric representation where amplitude is 1. So if you chop this frequency axis and if you rotate it by 180 degree, the amplitude will become 0.5, which is represented as a half. You'll get this representation which correlates with your Euler identity. So both the representations are the same. So here, if you are having one-sided spectrum, it is a trigonometric spectrum, while two-sided spectrum is an exponential spectrum, and there is no difference at all. If you flip left-hand side of this exponential frequency domain about y-axis, they will superimpose, and the 0.5 plus 0.5 will become 1. So there is no difference in trigonometric frequency domain and exponential frequency domain. But exponential frequency domain representation simplifies a lot of mathematical problems, and that we'll see in our subsequent lecture. We'll see a simulation in MATLAB for impulse function and exponential function. So impulse function, we have written a simple MATLAB code. So these are the parameters for sampling frequency and sampling time. These are the number of samples. Now we made the center value equal to 1, which simulates your impulse function. And then we plotted along with its Fourier transform in the second graph. Now if you run this, you can see the impulse function with pulse width 0. Now this is simulated in a discrete time domain, because on computer you cannot implement analog signal. You can implement only the discrete time version of the signal. So here you'll find amplitude is 1 and time width is 0. Now if you take a Fourier transform in the second graph, you'll see the spectrum is a flat, which value is 1. So what it represents, it has all the frequencies with equal magnitude or equal energy. So impulse function forms a very important model in analysis of system. So if you apply impulse function to input of a linear time invariant system, the output response is called impulse response, and it represents transfer function of the system. So to evaluate a transfer function of the system, the simple idea is apply the impulse function and see the output, which is a time domain representation of transfer function of a system. So it forms an important signal in the analysis of the system, which we'll see in detail in our subsequent lecture. Now we'll see the second simulation for exponential function. Now here, again, these are the initialization parameters, sampling frequency and number of samples. These are the two exponential functions. Here we introduce the scale factor A, which is also called attenuation factor as 0.05. And there are two exponential functions. One is exponentially increasing and second one is decreasing. And now third one is the complex exponential function with a negative frequency, because here we multiplied it minus j. So you'll get a impulse at a negative frequency. Now when you run this simulation, you can see the simulation results. The first one is a exponentially increasing function, and below that you'll find corresponding Fourier transform or frequency spectrum, which shows a low pass function. Exponentially decreasing function also has a spectrum which is a low pass function. If you see the complex exponential function, then it represents circle as we saw in our theory. So we'll rotate and we'll see the different physical view of this function. So if you draw in a complex domain, that is a real and imaginary part, so it represents circle as we saw in our theory lecture. If you draw with respect to time, okay, so now here you can see the time axis, real magnitude axis and imaginary magnitude axis. So you can draw with a time and one of the axis, real or imaginary. You can see this one represents a sine wave. Similarly, we can go for a real axis and you can see it represents, and in 3 domain as well as circle. So here represents circle, while in time domain it represents sine wave. So e raised to j theta or e raised to jx, whenever it is a function of time, it represents a sine wave in an exponential domain. Now, if you see here the frequency spectrum of e raised to minus j theta, it shows a negative frequency, right? Because we multiplied with minus 1. Now here, if you change this to plus 1, and if you run the simulation again, then here you can see the frequency spectrum of complex exponential shifted to the positive value because it represents positive frequency. So this is all about exponential function as an introductory part, and I hope you must have enjoyed this lecture, and thank you for watching my show.